This is reverse combustion. Information given is actually at the towards the product. Okay, the product itself. Okay. Alright. So we're gonna continue with a new example, which is this is example for reverse combustion analysis. Right. In the previous video, I explained to you how to balance combustion equation. Right. And the information given is actually at the fuel side and air side. Right. And after that, you do balancing to the product. Okay. But this is reverse combustion. Okay. Is different. Information given is actually at the towards the product. Okay, the product itself. So how do you balance this one? Is actually to find how much the fuel is used and the air, right? So let's see the example. Okay, you might want to pause your video. Okay, with the example. Okay, you have the fuel is obtained C8H18 and it is burned with a dry air. Okay, and the product, okay, on a dry basis is 10%, 10.02% carbon dioxide, 5.62% oxygen, 0.88% CO, and 83.48% nitrogen, right? So you have to determine the air-fuel ratio and the percentage of theoretical air use. Okay, so let's write down the combustion equation. So this one will be equal to the percentage of the product, right? So it becomes right. So let's perhaps I'm going to explain about product, right? So if you can see, this is product. So if we add up all 10.02, 5.62, 0.88, and 83.48, it's actually 100%. Okay, we don't know the exact value, right? But we know in terms of percentage. So the product is actually 100%. 100% of product which is on a dry basis, right? What I mean is, okay, suppose since you have hydrogen, right, in your fuel, and you add up with water, so basically, I mean oxygen, so you need to include another one, right, plus a portion of water. Alright, H2O. This is how combustion product looks like. Okay, it's gonna have a water as a part of the product. So now what we need to do is balance this equation. Find the x, A, and as well as B, right? So let's start with nitrogen and 2. So meaning we have 3.76 A. 3.76 A equals to 83.48 nitrogen, right? So therefore A is actually 22.20. Now replace it with carbon. Carbon we have 8x and then 10.02 C, 0.88 C right here. So meaning so from there you can determine the value of x. So x here is 1.36. We go to H, same approach. Therefore B is equal to 12.24. And then the last one is oxygen. Okay, so now you have A, oxygen, O2, O2. So since O2, this one become directly A, become A, and then equals to 10.02 plus 5.62. This one is 0.88O. Okay, not oxygen. Not O2. Our approach is actually O2, so meaning we need to divide it by 2, right? So this one plus 0.44 and plus another one, which is this one, B divided by 2. Right? So B divided by 2, meaning this value 12.24. So from there, we're going to solve that. So meaning A is equals to 22.20, which is to prove this is actually the same with this one. Alright. Okay. So now we know we have all the unknowns. Okay. A equals to 22.20, x equals to 1.36, b equals to 12.24. So what we're going to do next is we are going to substitute all these unknowns into the main equation. Right. So it's going to become 1.36. C8H18 plus 22.20 O2 is 3.76. And the product is 10.02 CO2. 2 plus 0.88 equal 5.62 into and then plus 83.48 into and 12.24 which is right. Okay, so this is the balance equation from the reverse combustion. Okay, we have information from the product side, right? So from there we still can balance, but we call it as a reverse combustion analysis. Alright, so this equation, let me take this opportunity to explain about this one. So in practice, normally we want to know how much 1 kilomole of fuel producing a fraction of product, right? So this one is actually 1.36 kilomole of fuel acting up together with the air, alright, combust together with the air. So what happened if you want to know 1 kilomole, right? 1 kilomole of fuel. So if 1 kilomole of fuel, okay, let's see what happened to this equation. So what we need to do is we just need to divide R with 1.36. So this one is going to end up with C8H18 plus Alright, so this is what happens when you have a 1 kilomole of fuel. Fuel meaning C8H18, right? So this is the balance equation. Okay, so number 1, the question is the air fuel ratio, right? Find the air fuel ratio. So equals to mass of air divided by mass of fuel. So here you have 16.32. This is, you know, mass is actually m air divided by fuel. So the number of moles is 16.32. Multiply with 4.76, O2 plus into, and then multiply with the molar mass, 29. Okay, similarly, so we have carbon and hydrogen in our fuel. So C8, 8 multiplied by the molar mass of carbon, 12 plus 9, right? 9. Since we use hydrogen, so instead of 18, it's actually 9. With 2. So from there, It's actually 19.76 kg. So that is the air to fuel ratio for the case of 1 kilomole of fuel. Okay, number 2 is to find the percentage of theoretical air used. Okay, find the percentage of theoretical air use or needed. Okay, in order for us to find the percentage, okay, so I'm talking about percentage of theoretical air. So we need to know the theoretical air itself. How much does it need? So in order for us to find the amount of theoretical air, is actually we need to analyze what we call as a theoretical combustion. Theoretical combustion, right? So theoretical combustion is basically just amount of 1 kilomole of fuel plus the amount of theoretical air needed, producing the theoretical amount of product. Okay, it's actually only it's actually in just nicely for theory, in theory. Alright, it's not an actual. Perhaps in actual, the fuel is not going to be 1 kilomole. The fuel may be perhaps 20 kilomole. Okay, but in theoretical combustion, all of it is actually 1 kilomole of fuel plus the exact amount of air needed, which is theoretical air, and the product is going to be theoretical product based on those combustion reaction, right? So for this fuel, C8H18 plus, so now it's actually ATH. Before this, I'm using A. ATH represent theoretical air plus O2 3.76 N2. Okay, so this one is equals to, so what is the product of theoretical combustion? Okay, basically is, since you have carbon and oxygen, so of course you're gonna have CO2. And then plus H2O. Okay, the reaction of hydrogen and air, from the fuel and air, and then plus we have nitrogen, right? So this one is actually nitrogen. Okay, so this one is gonna be the reactant, and this one is the product, right? Same like before, but the thing is, what I'm trying to explain here is just nicely for 1 kilomole of fuel and the amount of value needed to combust the 1 kilomole of fuel and produce this kind of product. Okay, let's see. So we're gonna have what we call as X here, right? So this is X, this one is Y, this one is P, right? Okay, so let's make this one a little bit faster. So for theoretical combustion, the amount of carbon dioxide at the product, okay, so this C, okay, you just put the numbers of C, the number of mole at C from the right hand side. So basically now it's directly become 8, follows this one, 8, this one is also 8. And then for H2O, we're going to use H2. So this one is H18, and this one become directly 9. Okay. And for N2, it's going to become 3.76, right? 3.76 multiplied with ATH. So this one is going to be 3.76 ATH. So that's how theoretical combustion looks like. Okay. So the only thing now is actually to find the value of ATH based on our theoretical combustion. Okay, so we can find ATH, A theoretical, either using O2 or N2. Okay, so let's use N2. O2. So for O2, ATH is actually equals to, this one is O2, 8 multiplied with ATH, this one is O2, so meaning 8. 8 plus, this one is O, right? So meaning 9, so we need to divide it into 2. 9 divided by 2. Okay, from there, so therefore ATH is equals to 12.5. Okay, so therefore percentage of theoretical air is actually equals to mass air, not mass fluid, this mass, and mass of air pH. So meaning and air divided by and air pH. So this one equals to 16.32. Right, this value 16.32 from 1 kilomole. Okay, so since this is also 1 kilomole, so you need to use 1 kilomole, right? So 16.32 multiplied with 4.76. Yeah, we can also multiply with M, but the thing is both are the same, right? So no need for that. Divide by 12.5. So this time is ATH. Multiply with 4.76. So from there, it's actually 121%. Right, done. So that is the to find the answer number 2, which is the percentage of theoretical air use. Alright, so that's all for this session.